Okay, so what I want to talk about today is the evolution of the atomic model. What's your name?
Several of them. It's Adam. So,
All right, so people have been thinking about this stuff called matter for a long time. And the most conscious, one of the reasons I'm going to talk about this is science. A lot of people don't know what science is. And they think it's an absolute. A lot of people think it's absolute. In other words, not changing. And I'm going to show you it's changed a lot. The science is taking data and making sense of it. All it is. If the data changes legitimately, then the idea about that concept is going to change. This guy named Democritus, Greek guy. And there were competing ideas back in Greece regarding matter. There was Democritus and Aristotle. Aristotle was definitely more popular in terms of his concepts than Democritus was. Democritus came up with the idea of the atom, not Aristotle. Democritus, atomos in Greek means no cut. So the concept is, well, I have an apple and I have two knives and I go like this. I keep chopping away until it's no longer an apple. That's where Democritus mentioned no cut, where the identity of that matter no longer is that identity any longer. As you cut it a couple times, it's still an apple. You can cut it a lot, and it still tastes like an apple. When you get to some point, though, very microscopically, where it's no longer an apple. And that's what Democritus is talking about here. Aristotle said, earth, air, fire, water. And his ideas lasted into the 1700s in Europe. Now, there are three areas of the world where this stuff is being thought about: Asia, Middle East, and Europe. Everywhere else, at least as far as we know, everywhere else, it wasn't really talked about. Okay. During the early days, there was a rise of alchemy. And alchemy was an early attempt to get at things like, what is gold versus lead? Can I turn lead into gold? Now, all the alchemists were the kings. And what do all the kings want more of? Wealth. At that time, it was gold and silver. So the alchemist's main job was converting lead to gold. Now, there's a problem with that. It's very expensive to do. We do that all the time nowadays. It's called transmutation, where you change the number of protons in an atom, which changes its identity and physical characteristics. We do that in a nuclear reaction. We do that in the atmosphere. We do it all the time. Transmutation. But it's very expensive, except the stuff done in the atmosphere. Yeah.
So it's like the equivalent to genetic modification.
Yeah, similar to that. Okay, there were some problems with alchemy, though. They didn't have nuclear reactors. They didn't have colliders. They didn't have all this horrendously expensive stuff or the knowledge at the time. They just were kind of pouring stuff together. And there were two main issues with alchemy. One was, in today's world, if you come up with some idea, scientific thought, you've got to be able to have someone else, another group, replicate that. If it's not repeatable, it's not valid. As part of the scientific method. They didn't do that in those days, so they could never prove anything because it wasn't repeatable. Okay, now there's another issue going on here. All the kingdoms wanted their alchemists to keep quiet. Don't share your information. Because that information was part of their power. Especially if they could convert lead to gold. Now, in early Europe, there were villages, not large cities, villages like Paris, London. Those were villages at the time. So 1100 AD, when one village wanted to talk to the other, there's only one way to do it. That's either walking or on a horse. So they couldn't communicate very easily from one village to the next. Another problem alchemists had is because of that lack of communication, they lacked a common knowledge. For example, water, common name for water, not in Mexico. What's the common name for water in Mexico? Aqua. What about in your country? Water. So it's different in every country because they didn't have a common knowledge base. A beaker is not called a beaker in another country. Yeah.
I was talking with one of my teachers one time that all the different labels on the elements are from specific that country. That's why it might not be the same letters as the actual word. You get what I'm reading. When they came up with the letters for that element, it was specific to one specific country, and that's why PB lead and not LD.
All right, well, it's got, most of the names up there are old names. Like Plumbus is
That's an actual thing?
Plumbus, yeah. You heard of a plumb bob?
Oh, yeah.
Okay, that comes from plumbers. It's plumber now. Begins with a P, uses a plumb bob because you wanted the pipes vertical. There's a lot of old words, derivations from that, yes. Okay, so not repeatable discoveries, not a common language. So because they didn't have a common language, it was difficult for someone to repeat something if they don't know what the guy's talking about. Now, all that is fixed in modern science. Because you won't be successful, period, if you don't follow the opposites of these. Now, a lot of people don't give credit for other parts of the world in terms of science. And it's totally unfair. For example, the Middle East, a huge program going. A long time ago, but they had a very large program, very sophisticated program. In fact, this guy was considered the grandfather of modern chemistry. China, another place. They invented gunpowder. Now, gunpowder is very simple to make. Very simple to make, yet they still discovered it. Along with spaghetti. So anyway, I want to give credit for these early people. They knew what they were doing. And they did not have a lot of the problems that Europe did. Now, not until early 1800 that this guy came along, European, and he came up with the first idea that was repeatable. Okay? He's talking about chemistry as we know it today, very early stages, but that's what he brought about. He also brought back Democritus' idea of the atom. He disproved Aristotle's idea. It was hard, just like politics now is hard to change. Same thing in those days. Nothing's really changed in terms of that kind of stuff. Okay. So remember, Democritus had the no-cut atomos idea, or the atom. This is what Dalton came up with. Now, 1 through 4 are true today, 5 is not. As he didn't understand nuclear chemistry at the time, and nuclear chemistry proves number 5 is not consistent. Okay, so matter is composed of individual atoms, particles. All atoms of a particular element are identical. Now that's like, duh. Piece of gold here and a piece of gold here. Gee, the atoms are identical. These are both gold. Different elements have different atoms. Here we have silver, we have gold. The atoms are not the same. Another duh. Now, number 4 is atoms combine in certain whole number ratios. What's the formula for water? H2O, not H2.10 or H1.90. It's exactly 2. And exactly 1 oxygen. Exactly. Infinite significant figures. Now, those of you who are rapidly writing away, I have this I was going to tell you, I have this, it's a PowerPoint slide. I'll put that up when I get to the lab. Anyway, so the main thing is if you want to take notes, that's fine, but you can just listen and grab the PowerPoint when you get back. Okay, so Dalton came up with these ideas, and Thomson came up with 2 things Thomson's known for. He discovered electrons. He called them corpuscles. And he also came up with the idea of the plum pudding model for the atom. So these are your notes. Thomson, electrons, plum pudding. All you need. He envisioned a particle had to exist that was smaller than the atom. So he came up with the concept that the atom can be divisible. If there's particles inside, that means you can divide it up. Again, they're called corpuscles. Now we know them as electrons. And he also indirectly discovered protons, positively charged protons, because the atoms were neutral, no net charge. That means if something's negative, you're going to have something equally but oppositely charged. So he came up with, there must be something in there positively charged. Millikan determined the charge of the electron. It was negatively charged, and he was able to actually measure how strong that charge was. The unit is called a Coulomb. So Millikan charged electron. We're really netting this out. Now, a guy came along, Rutherford, very famous guy, and wanted to validate Thomson's plum pudding model. So he devised an experiment to show that plum pudding model was valid. What he decided to do is he took a thin sheet of gold and he shot it with a particle. What he shot it with is an alpha particle. An alpha particle is a very heavy subatomic particle. It's made up of 2 neutrons and 2 protons. And as far as subatomic particle goes, it's extremely heavy. That was his bullet. He shot it out of a box with a hole in it, like a ray gun. But the weirdness is, now a plum pudding model is solid. So if you shoot something solid, like a billiard ball with another billiard ball, does it go through? No, it bounces, right? Well, that's what happened to 99.9% of the particles that he shot at the gold. They went through the gold. They didn't bounce back. So we went, "Ooh, that's not consistent with a solid model." So Rutherford came up with the idea that 0.1% that did bounce back, there's something in there that is solid. And all the mass of the atom is concentrated in that one tiny spot. It's called the nucleus. So Rutherford nucleus. Now he won the Nobel Prize not for this, on his nuclear chemistry work. He did win the Nobel Prize. He's not a dummy. Now think about this. This is really wild. If you have a stadium, a large professional football stadium, and on the middle 50-yard line, you have a marble. That's what size we're talking about. The atom is just tiny, tiny, tiny compared to the overall size of the atom. So basically, there's nothing in the atom except this little dot of mass. So I'm walking on nuts. Now let's go back 100 years or so. Everyone here is going, well, that doesn't make any sense. Think about 100 years ago. And he's saying there's nothing in the atom except this little dot of mass. That's a really hard concept to get across, particularly 100 years ago. So there's one other thing. Inside the nucleus are 2 particles, protons and neutrons. Neutrons have no charge, protons have a positive 1 charge. Now, what do like charges like to do? Positive to positive. Repel. Yet they're not being blown apart. They're together. So there's some very, very strong forces involved keeping them together. That's what you release during a nuclear reaction. It's that super strong force keeping those protons together. That's called the nuclear force. Very strong, very strong. Now, he didn't say anything about the organization of the electrons. Other than there's in the middle is the nucleus, and around it are electrons. No organization. However, well, Chadwick figured out that after weighing all the particles, it didn't add up. So he figured there need to be extra particles in there that didn't have a charge. So he came up with a concept of the neutron. Ashton came up with the concept of isotopes. Now we're going to find in a little while that the number of protons determines the element's ID. If you change the protons, you change the ID of the substance. So uranium has 92 electrons, protons. If we add an electron, it becomes neptunium. You add a proton, no longer uranium. So if the protons change, the element changes. But what happens if you change the number of neutrons? The element still is the same. Carbon 12, carbon 14. What's the difference? Carbon 14 has 2 extra neutrons. Still carbon though, because the number of protons remains the same. Carbon has 6 protons.
What does it do to the carbon when it changes?
The neutrons,
Yeah.
Nothing. It just weighs more. But the chemistry is the same. So isotopes differ in mass, but not in chemistry. Okay, Bohr, another new Nobel Prize winner. Niels Bohr is a very organized guy. He didn't believe that electrons were scattered around with no organization at all. He said there's definitely an organization to how the electrons are organized inside that atom. Now, remember the movie Back to the Future? What was on the cat's collar? Anyone remember? Remember? It was the universe on a little bitty token on the cat's collar.
So I think you're getting the movie mixed up. That was from Men in Black.
Men in Black, you're right. Thank you for that. Men in Black. Orion's collar. Okay, anyway, Bohr did not see that movie, obviously, he's very old. And he thought that the planetary system exhibited the same behavior as the inside of an atom. In other words, we had planets rotating around the sun, planets rotating around, electrons rotating around the nucleus. That was his concept. And he had a whole bunch of fancy math to show that that was consistent with certain properties, certain electronic properties of the atom. So we have a number of orbitals around the nucleus. Some are small that are close to the nucleus, and some get bigger as you go out. So the small ones can hold less electrons than the bigger ones. And he said, well, the innermost one can only hold 2. The next one out can hold 8. The next one out can hold 18. 8 plus 10. And then it gets bigger and bigger and bigger as you go out. And we're going to be using this concept a lot in here in Unit 4. Now, another thing Bohr came up with is this idea electrons are in a stable orbit. The innermost one is the most stable, As you go out, it's less and less stable. The reason why the innermost one is stable is because the nucleus is positively charged and the electrons are negatively charged and opposites attract. So that's why the inner one is more stable because it can get more attraction. However, what's in between those orbitals is nothing. And the electrons were required to be on that curved orbital. However, they could jump from one orbital to the other. Now, these fluorescent lights work on that principle. When we zap an electron on an orbital, we give it energy, it's going to want to go to another place that's consistent with its energy level, which is one of the outer orbitals from that one orbital that it's on. When it's unstable, it does that. So when we zap it, it moves electron to an unstable orbital, and it doesn't like to stay there because it's unstable. What happens, it goes back to the original orbital. When it does that, it gives off energy. That's what's happening with fluorescent lights. We fill it with an inert gas, and then we zap it with a couple thousand volt charge. So inside your fluorescent lights, there's something there called a ballast. That is a transformer that jacks up the electricity level voltage-wise and something very high. And that's what zaps the neon gas. So up the electrons go, and then it's unstable, so they come back down, and the energy given off is in the visible spectrum, so we see it. There's also energy in the ultraviolet that we don't see, and also in the infrared that we don't see. So all those are levels of energy. Only one of them we can see. That's the visible spectrum. Okay, so when the excited electron comes back down to the ground state, that's what they call it, before it's excited up, it gives off energy. Now, this is how they figure out what stars are made out of, because they give off light. And they analyze that light and figure out what frequency the energy is. And they can go back to a table and figure out what element is being burned to produce that. So Bohr did this. So Bohr came up with orbitals. He came up with the idea that electrons can move from one orbital to the next by injecting energy, and then the energy is given off when it returns to the ground state. Now, there's a problem with the planetary model. And so what we have now is the newest model. Now, this happened 120 years ago or so. Back, 120-ish, 110 years ago. Turn of the 1900s. That's when all this goes on. You've heard of Einstein. Many people, Fermi, Einstein, there's a number of physicists at the time said Bohr's model does not work. All that fancy math Bohr came up with only works for hydrogen. Doesn't work for anything else. Now, the problem is, there's a couple problems with Bohr's model. One, he doesn't predict the right configurations that atoms undergo when they combine. Also, the electrons to stay in an orbit require an energy. And if you don't give it energy, it spirals into the middle. And electrons don't do that. So those are the two main areas that Bohr's atom model failed. So we now have something called a quantum mechanical model. And it's totally different than Bohr's. They still talk about orbitals, but not in the same sense Bohr did. Thought about the planetary model. Quantum mechanics doesn't do that at all. Quantum mechanics is a statistical model. Let me give you an example of what they mean by that. So, on quantum mechanical model, they can predict where they can find electrons, just like in Bohr's model. Bohr's model said you can find electrons on a given orbital. Well, the quantum mechanic model says that there's a probability of finding an electron in a certain area. So, let's take Rayleigh's grocery store. On the side of the building, there's a place where smokers go. And when you go to that door, you find cigarette butts on the ground. You know how smokers are, they flick their butts. One thing my daughter and I don't have in common, smoking. My daughter smokes. She flicks her butts. Doesn't do it in front of me anymore, because I give her a bad time, but they flick their butts. When I was in the Air Force, we had something called a butt can. You smoke and you put your butt in the can, not to be flicked. So if we want to find a smoker, we know where to go. On the side of Rayleigh where the door is, because we know that there's cigarette butts there. So if we want to find the smoker, that's where to go. We're not sure how the smokers got there. Could be a customer or could be an employee. We don't really know, but we know where to go to find the smoker. That's what quantum mechanics is. We know where to go to find electrons. And there's some very fancy math. I took quantum mechanics at Davis. It was a whole quarter long, just like quantum mechanics. And it's very fancy math. That's why you take calculus to become a chemist. Because of it's something called physical chemistry. Okay, and quantum mechanics came up with this idea of there are four things that we can do for configuring an electron's configuration. Now we're going to get into this in Unit 4 big time. I wanted to give you an idea of where we are right now in terms of the atomic model. So we still got the nucleus. Protons and neutrons are in the nucleus, and we have electrons around the nucleus in well-defined statistical areas. Now, again, when I say statistical, that's what are the chances of finding an electron? For example, what are the chances of finding in this building trash outside the door? Small or large? Really small, right? People go and pick up the trash and all that stuff. But the odds are still there that there's trash out there. Small, but trash out there. Yeah.
And then there are things that increase the probability, like kids walking by or like there's an event.
Yeah, and so possibly by the trash cans, you might find more straight trash that people missed when they trying to throw things away. Well, that's the concept of the statistical model for the atom. It's very, very different concept. And it's been around a long time, over 100 years. But it's got some good agreement with what the world is supposed to be in terms of elements. Okay, now I'm going to leave it there. I'm going to pick up on Unit 4 right here. So I'm going to talk about Okay, so this is the periodic table, as all of you remember. Now, Mendeleev, a Russian guy, organized the elements at the time into this periodic table. And secondly, he published that finding. There was a geologist before him that came up with the same idea, but he didn't publish. So in science, publish or perish. So Mendeleev is remembered for developing the concept of the periodic table. And that geologist is nowhere to be found. Okay. One of the things about the periodic table is each element is inside of a square. So let's choose carbon, for example. And there are two numbers also associated with each element. There's an integer and a decimal number. Now, the integer is the number of protons, and it's also called the atomic number. This is the symbol for carbon. Now, there are some elements have two letters to the symbol, others have one. Now, what's critical, no exceptions. Let's look at chlorine. If there are two letters for the symbol, the first one has to be uppercase. The second one has to be lowercase. No exceptions. Let me show you why that's important. There's an element called cobalt. CO. There's also a molecule, CO. They're not the same. One is carbon monoxide, the other is cobalt. And we know cobalt because it's got a lowercase o. So this is an example of why you have to do it like this. First letter is uppercase, second one is lowercase. Okay. Now this decimal number here. We're going to be getting into that big time in unit 2. The big time unit, this is called the this is called the atomic mass or the molar mass. And that is the number, and the reason why it's a decimal and not an integer is because it's taken all the isotopes. Remember, isotopes differ in the number of neutrons, all the isotopes in the world, and weighed them. And they got an average of 12.01 for the average mass in the world. Okay, now remember, carbon has 2 isotopes. Actually, it has a whole bunch, but most common ones are carbon 12 and carbon 14. Which weighs more? Carbon 12 or carbon 14? 14 weighs more. That's why it's a 14 is bigger than a 12. But there aren't very many carbon 14s compared to carbon 12s. That's why the average is closer to 12 than 14. But it's over 12. 12.01. The 01 are carbon 14 isotopes. Okay, and the units of that are AMU's atomic mass units. Or grams per mole. Now, this is going to make more sense tomorrow. But atomic mass of carbon is 12.01. So those are the three things that every periodic table will have on it. Now, depending on what periodic table you're using, sometimes there will be the actual name of the element there. So I'm going to give you a periodic table tomorrow, which has the name in it, which is this one here we're looking at. Notice it, this one has name block. Now, in your next chemistry class, depending on your instructor, they may require you to memorize part of the periodic table, the upper part. I'm not having you do that because I don't believe in mass memorization, because you forget it as soon as you leave the class. And you have a smartphone, within 4 seconds, you can look up things. So why memorize it if you can look it up? But anyway, it depends on your next instructor. And they're all different. Okay, so that's the periodic table. Now, there's a little more organizational stuff we have to talk about regarding the periodic table. Okay, there are rows and columns in a two-dimensional table. The columns are called groups. And there's a whole bunch of groups. You're going to need to know 4 of them. Okay, and the rows, oops. Those are called periods or shells. Now, the reason why the columns are columns is because they have similar chemical characteristics. So every group has that bottom scribbles characteristics. For example, is it a liquid, solid, or gas? Does it react a certain way? And in unit 4, we're going to find out why that's so. It has to do with something called valence electrons and how those electrons are organized. But basically, they're in the group because chemistry-wise, they're very, very similar. And they all have names. Okay, so this one here is called the noble gases. They are very, very, very stable. So we have helium, neon, argon, krypton, etc. Very, 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 very stable. And because they're very, very stable, they don't react. Stable things want to stay stable. Unstable things want to become stable. So everything else is unstable in the periodic table, except for the noble gases. That's why they react, because they're unstable. They want to become stable, kind of like life. We all want to become more stable. So sometimes we react, it's called a relationship, and sometimes it makes us more stable, and other times it doesn't work. Okay, so first one you need to know are noble gases. Second one is halogens. Halogens. So noble gases, halogens, and over the other side, and come it. Those are called the alkali metals. These are called the alkali earth metals. Okay, there's two more things for now. We're going to talk about organizationally in the periodic table. So again, the noble gases are stable. Everything else is unstable. And they become more stable by reacting. All right. So there are three groups in general of elements. Those are called metals. Metals have characteristics. They're shiny, they're malleable, they conduct electricity. I mean, what's the opposite of metal? Yep, non-metals. And they do the opposite of metals. They don't conduct electricity, they're dull, and they're not malleable, they're brittle. Now, in one class up in Olympia, I taught a class very similar to this one. One of the labs, they had to determine whether what they were looking at were metals or non-metals. So one of the tests, we had an anvil there and a hammer. And they would take that quote unquote element and put it on the anvil and smack it with a hammer. If it shattered, it was a non-metal. If it bent, it was a metal. It was one of the tests. Okay, now, life is gray. We don't have black versus white in the world. We have everything in between. Same with the periodic table. You've got something in between metals and non-metals. That group there, along the black squiggly line, those are called metalloids. Oh, And they are partially metal and partially non-metal. And they change back and forth. In 1947, Bell Labs, AT&T now, Bell Labs in 1947 discovered the metalloids, did something very unique. When you applied a voltage to them, they either became a conductor or a non-conductor. When you applied a voltage to it, it can conduct electricity. If you did the opposite polarity of the voltage, it wouldn't conduct at all. Guess what they invented? Something called a transistor. First one was a diode, and they went to more sophisticated NPN transistors and a whole bunch of them. They invented electronics that did not use a ton of heat. Before that, everything was vacuum tube. Vacuum tubes are like little heaters. If you touch them, you'll get burned because they're hot. That's because there's a filament inside of them that glows and it boils off electrons. And when it boils off electrons, it's hot, physically hot. The first computer was developed during the very, very end of World War II. It was called the ENOC. And it was designed to figure out ballistic projectiles and these big giant guns on ships. It had like 15,000 vacuum tubes. It was the size of this room. Yeah.
Wasn't the first computer to break the
Like what?
machine? Wasn't the first computer the Enigma machine or made to break the Enigma machine during World War II?
It didn't use vacuum tubes though. Remember it used all those,
Oh, you're right.
the gears and all that stuff? It was big too. That was a good movie. Did you see the movie? Sad ending though.
Yeah.
Very, yes. In this big room were all these vacuum tubes. Well, they had to have another room this size to do two things. They had a huge air conditioner, and secondly, the power supply for all these vacuum tubes. So the computers in those days were huge, huge, the electronic ones. Of course, now we have, this has as much power as that huge 15,000 tube computer. Bell Labs, when they invented the transistor, all that heat bit went away. You can touch an LED, for example, light emitting diode. It's cool to the touch, it's not hot, even though it gives off light. So metalloids, very, very important. Okay, so that's it for now on the organization of the periodic table. So on the test, test 2, you're going to have a periodic table. I'm going to ask you to identify this stuff. Metals versus non-metals versus metalloids, halogens, alkali metals, alkali earth metals, etc. By the way, the periods don't have any chemistry in them. The only chemistry is things get smaller as you go across. And there are 7 periods at the moment until we discover more elements. Okay. Now tomorrow, we're going to start talking about grams and neutrons and a new unit that some of you have heard of, some of you not. Brand new unit. Okay, so that's going to be it for today. Are there any questions about what's going on? Look on the file, the lab and lecture schedule.